Okay, hi everyone, good morning. Welcome to Neural Computing tutorial. Right. As usual, can you hear me?
Yes.
Right. So this week, right, today, we'll be continuing for the forward automatic differentiation, right, that we did in class last week, Wednesday, right, just to check the answers. And then we'll start on the reverse mode automatic differentiation on Wednesday. Okay, so we'll do that on Wednesday. Now, just give me a moment here. Okay. So, last week we did the forward automatic differentiation um, exercise, right? So we have some functions here, and you are asked to complete the functions, the class dual number, and you are asked to complete the methods of it, the multiplication, the addition, the power, and all that. Okay, and then if you do that properly, all the operations properly, you'll see here that dual number here. When you test this statement, so the addition operation, and you have the division operation over here, and also you have the exponential. So this is the exponential methods, right? And then these methods will be okay, right? Your result will be something like this. Result is 1.0 plus 0.0 epsilon, because you have set all your derivatives to be 0, right? And all your values we want, right? So it should be as this one. So if you have implemented if you have defined your dual number class properly, or you have defined the methods in your dual numbers class properly, this statement should not, there shouldn't be any error for this statement, okay? And after that, you are asked to implement other max functions, right? So in this case, the sine of x. Of course, you are asked to implement the cosine, tangent, and exponential. Now, the tests for this are, you have to do it yourself, right? So something like, take a sine of define x as a dual number, then pass that through your methods, and it should be okay. Now you are given this problem. Uh, may I know what is the answer that you get? This is for the dzd of dx. Maybe I'll just delete this. What is dz of dy, and what is dz of dx, and what is z? So when you set uh, the derivatives, right? The other dot d value, right, or dx has 1, and dy is 0, you'll get dz of dx, right? And if you set the other way around, you'll get dz of dy, right? So what is the answer? What is your answer? Can anyone share your answer?
So Z is x dot y plus the sine of x, correct?
Yes, this one. Yeah.
Yeah, so
Z.
we're taking So we're taking the partial derivative of z with respect to x, right? Or are we taking the one with respect to y?
You can start with either. What is the derivatives of what is z
Mm-hmm.
and what is the derivatives of z with respect to x?
Since z is based on what I see, it could be a function of x based on our interpretation. If we imagine that, that would be the partial derivative of z with respect to x. And in that case, I think that would be just y plus negative cosine of x. But for the other way around, if we say that we're taking the partial derivative of z with respect to y, I think it would be just x plus sine x. Sorry, x plus that would be since it becomes a constant, x plus 0.
Mm-hmm. So what is the value?
For dz dy, I think is half. For the first one, hmm, for the first one, because we need sine x to be kept in the equation, and we're just deriving over that. Negative cosine of x. Let me calculate it real quick. One moment.
Um, calculation was manual calculation is okay as well. But did you get the when you put when you have defined the dual number class and you do your calculation, did you get the same values?
Yeah.
Just a moment, yeah. Okay, so the z for the values of z is 2.57, and yeah, it's a very long values, 2.5714255538604 all right. Your dz with respect of to x, right? Dz dx should be 5.07 7, and so forth, and your dz dy should be 0.5. Okay. Just be careful that your z should be the same for both dz and dz dx and dz dy. Right? Your z should not change.
Okay, doctor, thank you.
Okay, just take care of that. All right. So if you've done that, then it seems okay. Now, how do you define the power methods? So you have the addition, the division, the multiplication, the subtraction, and also the power, right? So how do you find that? So in putting in all together, right? We only use the multiplication and the addition, right? We only use the multiplication and the addition, but we haven't used the power methods. Now let's look at the power methods. Yeah? So in this problem, we only have x multiplied by y plus the sign of x, right? Oh, so you have addition, um, multiplication, addition, and also the sign of x. Yeah? So we have to define this. So how do you define your um, the power methods? Thank you for that. Thank you for that, Tingwei. All right. Okay, thank you. Mui Hao Zen. Mm-hmm. Okay. So this one is a bit tricky. Yeah? This one is a bit tricky. Some other answers. Yeah. So we have no other answers. I'll just demonstrate a little bit. Moiha, thank you very much for your answer. It's a good attempt, right? Ting Wei, if I'm not wrong, your answer is half of it. Yeah, there's another half of it. So, so what we're doing here, I'll show you the Jamboard, and then we'll done um, for today. So, so for differentiation rules, right? We're looking at we'll be looking at exponential, not exponential, the power, right? The power rules. Now, before we do that, just a moment, let me get my notes sorted a little bit. So what we're doing, right? We have x and y, right? Where x is a function of t, right? It's a variable dependent on t, and y is some variable dependent on t, right? And now what we have done is we have done given that z, for example, z equals f. Can you see my screen? Just to check, yeah. Can you see my screen that I'm sharing a Jamboard?
Yes.
All right, thank you for that. So, for example, right, you have additions, right? This is one. This is additions. Right? Addition. Now, for differentiation rules, okay, ini cek sebenarnya. Just 1 minute. Yeah, okay. So for differentiation rules, you are given, for example, the summation rule, right? For the addition operation. If you have two functions or of the same variable, right? So f is a function of x and g is a function of x, right? Then you see that if you are taking the partial derivatives of this with respect to x, you end up with the you take the partial derivatives of f with respect to x, and you take the partial derivatives of g with respect to x, right? So that's kind of simple. So you are given this, right? So you simply saying that if you are taking the partial derivatives, so you take if you are because of the sum rule, right? So basically we're saying because of the sum rule, right? What we're doing is dx, right? F of x y is equals to d of dx t. No, this is not x, this is t. So you just take the partial derivatives of x with respect to t plus the partial derivatives of y with respect to t, right? Now this is because of the sum rule. But if you think of it, right, if you think again that the summation rule, right, you can also kind of use the chain rule. There is some sort of a chain rule in here. I'll show you just a moment. So this is chain rule from Wikipedia. Yeah? So in our case, right, we want to generalize the chain rule, or we have to generalize the chain rule to multivariable functions, right? So we are looking at the chain rule of multivariable cases, right? In a sense. For example, as you can see, this chain rule here, if function f is addition, then you can derive a chain rule from here. So if we were to write it in this way, right? So before we come to this conclusion, right? We'll take this again to the chain rule. We can think this as derive this as a chain rule, right? Df of dx. I'll just write this properly. T, no, dx. This would be dx. Dt plus, right? Plus x y over d y d times dy over dt, right? And this is 1 times dx dt plus 1, right, times dy dt. Right. So when you have two functions, right? When you have two functions, that is, you have two variables, x and y, which is a function of some variable t, right? And then you have another function, which is another variable f, which is a function, is dependent of x and y, right? Then you can use the chain rule to kind of derive the sum rule, right? If you think of it that way. So for example, if you do f is a function of x, y, and z, then this is, and all of these are functions of the same variable, right? X, y, t, and z of t, right? So accordingly, if you are
program, it's 50D.
Deriving the partial derivatives of f with respect to t, you have to do, I'll just write it very quickly, right? So it's the x dt plus the f of dy with dy dt. And also this is there's another term that you have to add here, right? Because of the chain rule, right? As if, of course, as again, as if you're canceling this the numerator and the denominator, but we're not actually doing that, right? Because it's not, these are not fractions, right? So and as you add more and more variables, right? So as you add more and more variables, such as a1, a2, blah 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 blah, an, then your chain rule, the sum, just becomes a summation, right? So the f of da1 da1 over d t, right? So all of these a1, a2, and an, a1, a2, and an are functions of t, right? Functions of t, right? Plus blah 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 plus the f of d a n of dt. Okay, so we have become accustomed to that. If you are given a differentiation, then you apply the differentiation rules, right? But also in a way, in some way, you can also derive from the chain rule, right? In the case of multivariable functions. Now let's see the same way, in the same manner, right? You can also do for example, you can also do the for divisions, right? So f of x and y is equals to x t. Just write that properly. Divided by y of t, right? And so I'll just so please don't I'm just mixing up the notation. So if I write dx, this is also the same as I write this. Okay, the curly d's and just d's. I'm just using it interchangeably, the notation. Please don't mind. Yeah? Both refers to the same partial derivatives. It means the partial derivatives with respect to t. So here, right, then you do this, right, which is what is the partial derivatives of f with respect to x, right? This is y, 1 over y over t, 1 over y of t. Why? Because we are when we are differentiating, or we're finding the derivatives of one particular variable, right? For example, we're differentiating with respect to x, we'll always treat the other term as constant, as some constant. So that is the key here. That's the key why we can arrive to this conclusion. Yeah. So when we are differentiating with respect to x, we'll treat y as a constant. When we're differentiating y with respect to y, we'll treat x as constant, and so forth. And so you have multivariables, you have more, you have x, y, z, right? So if you are differentiating with respect to x, then you'll treat x and y and z as constants. So in this case, just continue here. Thus, so here you have to, you know, kind of do this, right? So x is a function of t, y is a function of t, right? And then if you do that, you know, blah, 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 you'll end up with the quotient rule, right? So you end up with this one. You end up with this. So I'm not gonna show this. So you need to verify this yourself, right? So if something goes yeah, n plus and divided by the squared term of yt squared, right? So this is division. Now let's come to our problem here. Just a moment, yeah. So we have the power functions. So f of x and y is x is a function. I'm just going to write it as x is a function of t and y is a function of t as well, right? No, not y. This is not product. So x is a function of t powered to y, which is also a function of t. Okay. I'm just writing the t's here for you know, for kind of a to be exact, right? You can of course you can write like this and write like this, and then you know says that x is a function of t and y is a function of t, right? Then what you want to ask yourself, what is the partial derivatives of x with respect to t then? What is this, right? What is this? Then by using the chain rule, right, you'll get again the same. This is the same, right? So if x y dx dt plus d of x y dy dot dy dt, right? Now here is where things get a little bit interesting, right? Now I'll take this as A and I'll do this as B, right? What is A? Which is what is the partial derivative of f with respect to x, given that f is a function of x and y. What is this? This is using the power rule. Yeah, this is using this one. So this you're using this rule, right? So x to the power of n. If you're differentiating it with respect to x, you'll get n times x and then to the power of n minus 1. Yeah. So in this case, we would be y and then x, y minus 1. Yeah. That's because of the power rule. And then you have a second term, right? You have a second term here. What is the partial derivatives of f with respect to y? Right? Which is the partial derivatives of f with respect to y. This is a little bit more, a little bit trickier, right? Because you have a function of x, right? Which is you have a f function of f is a function of x and y, but now instead of differentiating with respect to x, you need to differentiate with respect to y, where you know x is to the power of y. Now, what rules do we use here? What rules do we use here? We have to use the exponential. The derivatives of exponential functions. So if you have a to the power of u, right? So you have to do this, or in this case here, a to the power of x, and we're differentiating with respect to x, right? We're differentiating with respect to x, so it will be a to the power of x, and then you take the logarithm of a, right? And then in our case, because the y is a function of t, so we'll have this. So here we'll have x to the power of y. So this is the logarithm of x, right? And then if you put all of them together, putting it all together. So the partial derivative of x, the partial derivative of f with respect to t is equals to this term. So your power functions, right? Your power function in your dual number class should have this. So you have to implement this in the dual number class. Okay, so because when you put it together, right? When you have put you're putting it all together, you get this term, right? Now, if you look back at the Wikipedia page, this one here. This one. What I've done is also given here. Yeah. The case of exponential. Exponential here. Thing. So here is a bit, complicated, but it is more, the explanation is more general, right? So here for the case of multivariable case, the chain rule for the multivariable case, you have the arithmetic operations, and you also have the case of exponential, and you have multiplication as well. So this is we are doing for exponential, yeah, exponentiation. You have two, f is a function of u and v, equals u to the power of v, right? And then it follows if you are, but both u and v are functions of x in this case. So it follows that if you're differentiating or you're finding the partial derivatives with respect to x, then this is what you have to do. So this is the same as our answer here. Okay. So can anybody paste their codes how they implement this in the dual number class? Did you manage to implement this in the dual number class? So just be careful, yeah. Here, I'll just write here, exponential. Oh, yeah. So you, when doing for the power methods or the power functions, right? We not only have to do for the using you not only have to use the power rule, you also have to use the exponential rule, right? Because of the chain rule. We want to find the partial derivatives with respect to t here. Right. So, okay lah, I'll just share you my version, right? This is not perfect, yeah? This is not perfect. This is not perfect. So here, I have the power methods, right? And then what is the derivatives? So we have the x to the power of n, right? Or x to the power of y. I think this is a wrong comment. So okay. So it should be y minus 1. And the partial derivatives depends on which variable you are differentiating. So in order for me to avoid using, because in power functions, right, you are using the power function itself. You don't want that, because you are trying to override these methods, right? So I'm setting a and b equals to 1 and 1, and then I have a loop here. So this is actually implements the power functions. So it implements this part. Yeah, this is A, this is B. I'll just do some colors here in the dual number. So this is A. A is the calculation of x to the power of y minus 1, and B is the calculation of x to the power of y. But I don't want to use the power rule inside the power methods, because no, I'm the one to use the power functions or the power methods inside the power method, because we are obviously we are trying to override this method, right? So I have a for loop here to avoid using the same power functions or methods. So A keeps multiplication by itself, and then you have B as an extra term here. And here is the what I've written, right? So this is the x to the power of y. It's nothing new here. Only the derivatives is a bit complicated, which is this is an implementation of this term, putting it all together. This way of doing the power methods is, how should I say, it has its limitation. Can anybody guess what its limitations are? At least one limitation. There is one limitation here. Yeah, it's correct. Can we do power to the negative value, right? Or what if, you know, your power, you're taking square roots, for example, yeah? Your power to the fractions, yeah, 0.12 x to the power of 0.12 or x to the power of 0.13, then the for loops doesn't work, right? Then you have to take the root. So this only applies for positive integers, given that x and y's are positive integers, right? So the limitation is here is that x and y are positive integers. Okay, if you have any questions, does anyone have any questions? That is all for basically the materials that I wanted to share with you today, right? If you have any questions, please ask me. as I said, the implementation here isn't perfect. Yeah? This is not a perfect. It's just an example, right? Because I don't want to use, I want to avoid using the same power functions or same power methods in the power methods. You probably have a better implementation than mine. So you have, if there are no other questions, that's all for today. Thank you very much and see you on Wednesday.
Thank you, Doctor.
Welcome.
Thanks, Doctor.